Alright, in this video we're going to look at lines in R3 and then we'll solve questions 5 and 6 on the worksheet. Okay, so let's say we have a line L in three-dimensional space and we want to write an equation to describe the points on this line. Okay, so if you think for a moment what you need to describe a line in the xy plane, right? So in R2, well there you need a point on the line and you need a slope for the line. Okay, so what are the analogs of point and slope for this line L in R3? Well, we're going to need a point on the line, and I'll call this known point P0 and label its coordinates x0, y0, z0. And then I'll call the corresponding position vector R0. Okay, that's running from the origin out to this point P0. Okay, and then the analog of slope here is a direction vector for the line L. Okay, so I'll call our direction vector V and label its components A, B, C. And this is a vector that's parallel to our line L. Okay, so you can see our vector V here is parallel to L. Okay, so assuming we know this point P0 and a direction vector V for our line, let's say we have some other point, and I'll call that point P on our line L. I want to relate P to these knowns P0 and V, and here note I'm calling the corresponding position vector that runs from the origin out to P, I'm calling that the vector R. Okay, so how do I relate all of these? Well, the thing to note here is that since P0 and P are both on the line L, okay, the vector that runs from P0 to P is parallel to this vector V. So in other words, okay, the vector from P0 to P is a scalar multiple of this direction vector V. Okay, so there's some scalar t such that TV gives us this vector from P0 to P. Now notice here, if P is, say, off to the right, like you see in the figure, then our scalar multiple t here would be a positive number. Now if P were off here to the left, okay, then, right, I want the vector that points to the left, so our scalar multiple there, t would be actually negative. But in any event, okay, how can I relate these quantities now in the figure? Well, the position vector R, going from the origin out to the point P, is equal to the blue vector, right, R0, that's the position vector for the point B0, plus this scalar multiple of our direction vector, right, so plus TV. Okay, so this really feels like y equals mx plus b. In many ways it essentially is, except now of course we're working in R3 and we're doing this all in the language of vectors, okay, but there's certainly a lot of parallels there. Okay, so let's go ahead now and open this up in components, right? So R0, as we noted over here, its components are x0, y0, z0. Now TV, well, that's going to be t times the vector a, b, c, right? So if I combine these two vectors, I get a vector function for the line L. Okay, so R of t, this is x0 plus at, y0 plus bt, and z0 plus ct. Okay, and notice here, each of the component functions are linear functions of the parameter t. Okay, and so by combining, right, these linear relationships in this way, they in turn give us a description of this line in R3. Okay, and also just to emphasize, the coefficients of the parameter t in these equations, those are the components of the direction vector V. Okay, and we're going to see this in questions 5 and 6. And then, of course, these numbers out front, those are just the coordinates of our known point P0. Okay, so now that we have a vector function for the line, okay, we also have parametric equations for the line, and that's just reading off each of the component functions individually. Okay, cool. So now with all that in place, let's go ahead and look at question 5. I'm going to go ahead and make some space here. And up here in the upper right, I've just copied all of those equations we just derived for our reference. Okay, so 5a says find vector and parametric equations for the line passing through the points P, whose coordinates are -2, 1, 0, and Q, whose coordinates are 3, 4, -5. Okay, so I've drawn a picture here. And as we saw, right, the two key ingredients here are a known point. Well, here we actually know 2 points, so take your pick. And we need a direction vector, right? So a vector that's parallel to our line L. All right, so I'll go ahead for our direction vector and take the vector that runs from P to Q. Okay, so V is the vector PQ, and just subtracting coordinate-wise, we get 5, 3, -5. Okay, so this is our A, B, and C. And then for our x0, y0, z0, well, again, you can just take your pick from the coordinates of P or Q. I'll go ahead and use P here. And so -2 is our x0, 1 is our y0, and 0 is our z0. So you put that all together, right? R of t is equal to x0 plus at, so that's -2 plus 5t. And then we have y0 plus bt, so that's 1 plus 3t. And then finally z0 plus ct, so that's 0 plus a -5t. And that simplifies to what we see here. And again, the coefficients of t, right, those are the components of our direction vector v. And these numbers out front, well, they're just the coordinates of our known point. Okay, cool. So now one thing to note here, we could just as well use, say, the point Q, right, as our known point. So 3, 4, -5. And so if we do that, then these are the component functions we wind up getting. Now, these component functions are genuinely different than we're getting from this answer where we use P as our known point. Okay, that's not a problem, but the thing you do want to be careful about here is that this T that you see here in blue, right, when I'm using Q as my known point, is actually different than this T here in our first solution, right? So in our first solution, notice when T is 0, right, I'm at the point -2, 1, 0. Well, in other words, I'm at the point P. And when T is 1, I am at 3, 4, -5. So I'm at the point Q. So for our first solution, when T is 0, I'm at P. And when T is 1, I'm at Q. Okay, now in this second solution, when T is 0, I'm at 3, 4, -5. So I'm actually at Q now. So for what value of T am I going to be back here at P? Well, since I'm still using the direction vector V, which points in this direction here, right, I'm actually going to want a negative value of T. And of course, you can see easily that I want T here to equal -1. If I plug -1 in for T, I'm going to get -2 for X, 1 for Y, and 0 for Z, right? So I'm going to be back here at P when T is -1. So that's the one thing you do want to be mindful of. Perfectly fine to do it this way, but this T and this T are in fact different. Okay, cool. So now, continuing with this solution, the corresponding parametric equations, again, you just read those directly off of the component function. So there we are. All right, so then for part B, it says, find an equation for the projection of the line in part A onto the xy plane. Okay, now notice here it says an equation. So presumably they're looking for a Cartesian equation, so not parametric equations for the line that we get when we project our line here from part A onto the xy plane. So for the projection, well, as we saw in question 3, right, to look at the projection on the xy plane, we just essentially want to ignore the z coordinate, right? So just pay attention to what's going on with the x and the y coordinates. So here x is -2 plus 5t and y is 1 plus 3t. Okay, and since it says find an equation, let's go ahead and eliminate the parameter. And so using the x equation, right, t is x plus 2 over 5. And I'm going to plug that in for t in the equation for y, and then rewrite a bit, and I get y is equal to 3/5 times the quantity x plus 2 plus 1 as an equation that describes the projection of our line in part A onto the xy plane. Cool. All right, and then for part C, it says find vector and parametric equations for the line segment from the point P to the point Q. Okay, so not the line that passes through the points, but just the line segment that starts at P and ends at Q. Okay, well, we can use our same answer from part A. It's just now I need to put bounds on T. Okay, so as we already noted, when T is 0, okay, I'm located at the point P, right? When T is 0, x is negative 2, y is 1, and z is 0. And then when T is 1, right, I'm at my endpoint, right, Q. So that's going to be, right, when T is 1, 3, 4, negative 5. So letting T take on values just from 0 to 1, that's going to describe the points from P to Q only, right? So it's describing that line segment, not the line that passes through the points P, Q like we had in part A. Okay, and then here are those corresponding parametric equations. And there we have it. All right, cool. So now let's go ahead and do question 6 real quick. This one is a little bit faster. It says, find vector and parametric equations for the line parallel to the vector v. That's equal to 4i minus 3k, and passing through the point P with coordinates 0, 5, negative 7. All right, well, here, right, our A would be 4. That's the I component of our direction vector. Our B is 0. That's the J component of the direction vector. And our C is negative 3. That's the K component. And P here, right, these coordinates, those are our x0, y0, z0. So just as we saw in question 5, we put that all together as follows. So our vector function r of t, this is x0 plus at, so that's just 4t. And then this is y0 plus bt, so that's just 5 in this case. And then we have z0 plus ct, so that's negative 7 minus 3t. And there's the corresponding parametric equations. And that does it. All right, great. Thank you so much.